Okay, good morning. Let's get started. As you probably saw, I posted the grades on the Blackboard. It finally came back to life instead of staggering around like a zombie. So you should have been able to see your grades. The class average was about, I think, a 64, your raw score, and then the group score average was 89, so your grade somewhere in between that, which is a class average of 77. So that's a pretty decent score for the average. If you don't understand what your grading options are, just go to Blackboard. There's an email about that tells you what your options are. And if you still don't understand it, come see me about it, and we'll talk. The other thing we need to talk about briefly is there will be a set of assignments coming on this next week and a half, because we're having several people interview for a cell molecular position. And so I posted that on Piazza, and so look at those assignments. Probably by the end of the day, I'll post the actual assignment on Blackboard, but it's basically you go and attend those job seminars. You're going to help determine who the next faculty member is by telling me who you like and who you don't like. So the next 3 department seminars are all cell molecular related. They're either micro or virus type people that study these different things, and that applies to most of you in the room today, because a lot of them are sick. So go there and see what the new data are. So attend those, and let's see if there's something else. Well, I'll think of it. And so where we are today is we have just a little bit to finish up with membrane dynamics, and then we're going to start using all those proteins that we just talked about to do something useful, that is transport. So we'll get into that today. But let's finish the dynamics part up just a little bit. This, again, should be reviewed. This is covered in that background material. But you need to understand why is it important that fluidity of the membrane remain high, and what determines the membrane fluidity. And also, however fluid the membrane is going to determine how fast the proteins move in there, and can we determine how mobile proteins are. So we're going to cover a few more techniques sort of to add to our toolkit. So basically, you probably realize that phospholipids can move in certain directions only. They can diffuse in 2 dimensions, this way and that way. They can rotate. They have extremely fast vibrational frequencies that keeps the membrane really moving around. But what they can't do is they can't flip-flop from one leaflet to the other. That's like so if you had this guy and he wanted to flip-flop down to here, the polar head group would have to go through this sea of lipid, and energetically that's not favorable. So that rarely happens. In fact, when we want proteins to do that, we actually use a transport protein, a type of transport protein that can help flip them from one side to the other. Okay, so fluidity is important. Remember what determines phospholipid fluidity. Okay, there's a few key things, and it all has to do pretty much with the type of tail, the fatty acid tails they have. So just quickly to go over the review, you can look at that background, but the longer the fatty acid chain, the less fluid the membrane. Okay, so fluidity decreases as the length of the chain increases, right? And what's a good measure of fluidity? Well, a really simple one is melting point. The lower the melting point of a membrane, that is the phase transition from a gel to a sol, the more fluid the membrane. So high fluidity means low melting point. And I'll give you an example here in just a moment to show you that. So the length of this is important, and really important is whether it's saturated or unsaturated. If it's saturated, it's going to look like this. The legs are going to be kind of straight. That means they can pack together. That increases the melting point, decreases the fluidity. So saturation is less fluid than unsaturated. And so these guys all have, both of these have a single double bond there. Look what it does to the structure of the fatty acid. It gives it a kink. And so when this thing rotates, what's it going to do to its neighbors? It's going to kick them in the knee, right? And so it's going to make the lipids become very fluid and disoriented. That increases the fluidity and drops the melting point. So is there a technique that we can use to measure melting point? Absolutely. It's called scanning calorimetry. What happens is if you're measuring heat absorption, as you go from a gel into a salt, so you go from you can think of it as a solid into a liquid phase. There's at the peak that transition occurs at, there it's called the melting temperature. There's a large increase in the heat absorption. So if you can measure heat absorption, that's what a calorimeter does, heat absorption. And I think the units are kcals per mole. Okay, as a function of temperature, so 0, 20, and 40, 60, and let's just keep going, 80. This is degrees C. What happens is you'll see an increase, and then where it melts, where it goes from solid to liquid, that's the melting temperature, you'll see a big peak, and then it'll fall off. So everything on this side of the curve is a solid, or as we call it in membrane language, gel. Okay? And everything on this side of the melting temperature, it is called the T sub m, the melting temperature. Everything on the right side of that is a sol, that is a liquid. Okay? Now let's consider two molecules that have the exact same number of carbons, and that's oleate and stearate. Okay? Oleate and stearate. And I'm not into people memorizing structures of fatty acids, but this one's very illustrative. Okay, they both have 18 carbons. Okay, and you know that if we're going to compare them, they need to have the same carbon length, because if you change the carbon length, that's going to move the melting temperature around. Okay, but let's say this is an interesting sort of natural test case. So oleate has one double bond, so it is unsaturated. And stearate, which has the same number of carbons, is completely saturated, so it's got a very straight tail. And so based on what we've just been talking about, you would say the guy with the straight tail has a higher melting point, correct, and has lower fluidity than the one that has the little kinky tail and can, dance halls, kicking his buddies and keeping the membrane fluid, right? So what's going to happen is you would predict that oleate's going to be up here, and that's actually true. It's got a 16 degree TM, melting temperature. Just one double bond causes oleate to shift over here, like this. So this is stearate, and the melting temperature is 70 degrees. One double bond makes that big a difference. So you can imagine what would happen if you put two double bonds. Which way is this melting temperature going to go? The left, right? It's closer and closer. It has a dramatic effect. Okay? And then let's say we compared stearate to some protein, maybe, or a fatty acid like palmitate, which I think it has a shorter tail. So if this is stearate, which has 18, and palmitate has a shorter tail, where do you predict its melting temperature would be? To the left or to the right of stearate? Shorter tail, more fluidity, lower TM, so it's to the left. Okay. So the length of the tail and the number of double bonds is going to determine how fluid the phospholipid environment is. Doesn't necessarily determine how fluid the proteins are, but one influences the other. Okay. So that's a real straightforward thing. And then, of course, what does temperature always do to fluidity? It increases it, right? So that's a really fundamental thing you have to understand. Now, can you get too fluid? Absolutely. If you heat it up too much and the membrane's all bubbly, the proteins will be ejected, they won't work properly. So too much fluidity is just as bad as too little in a frozen membrane. You don't want either one of those. What molecule can we put into the lipid bilayer that acts as a fluidity buffer? Cholesterol, right? Because cholesterol is really amazing. It's got, I don't know if I have a picture of cholesterol. I thought I did. Okay, well, it's actually in the background. So cholesterol is interesting because its polar head group is a single hydroxyl. And what that does is, at high temperatures, what cholesterol does is it lowers it decreases the fluidity. So as the temperature gets high and the membrane starts to be too disruptively fluid, cholesterol reduces that fluidity at temperatures above the melting point. Okay? And the reason, there's a couple of reasons. One is the small head group allows the phospholipids on either side of it to pack in tighter. So if we look at this guy, okay, so cholesterol can just stick right in between these two, and these two on either side can get really close, and the closer the packing, what happens to fluidity? It decreases the fluidity. So as you start to overheat the membrane, cholesterol keeps that from becoming too fluid. Also, the sort of stiff steroid nucleus adds rigidity and stiffens the membrane and decreases the fluidity. Okay? What happens at low temperatures, animals that live in the Arctic, they actually have a lot of cholesterol in the membrane because below the melting temperature, what happens is the cholesterol increases the fluidity. The steroid nucleus has an aliphatic chain, and those two together, what they do is they disrupt the fatty acid tails in the really hydrophobic area of the membrane, increasing the fluidity. So cholesterol is important because it is a fluidity buffer at both ends of the spectrum. Okay. All right, so that's all covered in the review or the background material. Okay, what else do we need to talk about? So those are most of the things that determine the phospholipid fluidity. Of course, you can actually measure the fluidity of membranes, and you can measure the fluidity of proteins inside the membrane, okay, or within the membrane. So a technique to do that is called fluorescence recovery after photo-bleaching, and so it's called FRAP. And what you can either label lipids or you can label proteins. Let's label the lipids. I think that's what's done here. So you have to label the lipids, a population of lipids that you're interested in, with a fluorochrome, a fluorescent molecule. It needs to be very small relative to the molecular weight of what you're looking at. So it just needs to be really small, and we can get very small things that we can measure and attach them to lipids. Okay, so this is, we've attached a green fluorochrome, so under laser light this looks green, or under the microscope it looks green. And what we're going to do is a laser allows you to send a very small, highly proscribed area of laser light at that cell. And so you can actually bleach a specific patch. And what happens is when the laser light hits this type of fluorochrome, it irreversibly bleaches it. In other words, it extinguishes the fluorescence of the fluorochromes that are in that little patch. They are permanently bleached. They cannot recover their own color. All right, they're turned white. But if you turn off the laser, what you'll notice is after a period of time, the fluorescence becomes to turn green again in that area. And you can actually measure the return of fluorescence using various methods. So if you measure the fluorescence in that bleached area, it'll look like this. It's green, 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 and then you hit it with the laser and it bleaches, right? Because you're just measuring the fluorescence here. And then it's going to recover, because what's going to happen is molecules on either side of those bleached molecules displace them, and they start to move into the area previously occupied by the bleached patch. And so the recovery is caused by molecules diffusing laterally into that area. Okay? So you can actually get two types of information from this. The speed at which this recovers, this recovery speed, tells you the rate of diffusion of that population of molecules. Now you're not tracking single molecules, you're tracking a population of molecules. So it tells you what the average rate of recovery is, and so you can take a first derivative of this slope, and you can eyeball to tell how fast these go. So if it goes up there really fast, it's going to have a really steep rise, and this is another one of those square hyperbola things, okay? And if it's slow, the slope is going to be really slow, and it'll take a longer time to reach the recovery. Okay, so that's one type of data. How fast does it recover back to the highest point it can go? The second thing this technique tells you is the extent of recovery. Some of these, so if you label different proteins, what happens is you'll notice some of them completely recover. If it goes back to the starting point, that means 100% recovery. That means that population of proteins that you've labeled has 100% of mobility in the membrane. There's nothing to keep them attached to anything. They're completely free and random to move. Now, if it reaches less than, let's say it goes up to 50%, let's take it different. It goes up to 70% of the total amount of recovery. What does that mean? It means that 70% of the molecules are free to diffuse, 30% are attached to somebody. They're actually bound to something that's keeping them immobile. So the percentage of recovery tells you how many of that population are free to move and how many are not. Okay. And so those are two different, useful types of data to get when you're looking at different proteins. So you can either label the membrane components or you can label the protein and assess the fluidity of that population. All right, so let's just do a quick exercise. This is not a clicker question, but if you're going to, let's say you're looking at the fluidity of, or the mobility of two proteins, what's the very first thing you need to consider? Just it's going to determine how fast diffusion moves that protein. What's a big determinant of diffusion, rate of diffusion from high school? Temperature, yeah, that'll affect the fluidity of the membrane. Sure, it will. Temperature's big. Concentration, right? But if you're comparing diffusion rates of two different things, what's the first thing you need to ask? Size, molecular weight. Because the rate of diffusion is inversely proportional to the square root of the molecular weight. So the bigger the protein, the slower the diffusion. So it's not fair to compare two different proteins of different molecular weights unless that's the only difference between them. Let's say let's take two proteins so we're going along, this is the fluorescence activity, and this is time. Okay, and so we're going to bleach here, right? So it's going to go down, and then we're going to look at two different proteins. We'll take a blue protein and a purple protein. So blue is big, and purple is smaller. Okay. So you would predict that blue is going to lumber and take forever to get back up here. And remember, it's going to go back to 100% because the first condition was 100% recovery. That means it's not going to bind to anything. We're going to talk about what you look for when it binds to stuff. Okay, so that's where the blue recovery. Purple, the difference between the two is going to be same recovery, but look at the shape of the curve. It's much more steep. Okay, so understand that fundamental principle that you really got to compare apples to apples and oranges to oranges if you're asking something else about the membrane, like what's causing it not to recover to 100% or some other thing. But let's consider the other thing you need to know is the nature of the way it's in the membrane. So let's take a different example where let's take alkaline phosphatase and let's compare that to glycophorin. And let's just say, this is not true, but let's say the molecular weight of those two proteins are exactly equal. All right? Now think about the structure of those two proteins. You may have to look at your notes, I don't know. But if you know what they are, what class of membrane protein is. Now, let's say they have the same molecular weight. Which one, and let's give them both 100% recovery. There's nothing, because that levels the playing field. same molecular weight, nobody binds to something weird, they both go to 100%, which one's going to get there faster? We'll do red and we'll do green, okay? So red's going to be alkaline phosphatase, okay? And green is going to be, it's the axes, unfortunately, but it's also, green is glycophorin. Okay, so think about it. Which one's going to go faster? Or are they going to go at the same rate? What type, so the way you always think about this, and this is, I want to teach you how to think about the problem, is you have to know the class of membrane protein that you're talking about. Glycophorin is what? What type of membrane protein? What's the first category you put them into? Peripheral and integral. They're both integral membrane proteins. Glycophorin is a single pass. Okay. What type of protein is alkaline phosphatase? It's integral. There's a lot of different kinds of integrals. What about prions? What about variable surface glycoproteins? How do they fit into the membrane? GPI, but the category is lipid anchor. Okay. Now, is it on the outside of the cell or the inside of the cell? Alkaline phosphatase. What is it? So this is where when you're making that poster child card, you need to know what the function is. That's going to tell you. That's going to answer that question for you. Alkaline phosphatase waves around in the gut lumen and it slices off phosphates. It can't do that on the inside of the cell. It needs to be a membrane-bound lipid or protein that's facing the gut lumen with its foot in the exoplasmic leaflet. So you need to know the structure, you need to know what type of lipid it is, and what its function is to be able to answer this question. Okay. So it is a GPI anchored protein. Now, which one's going to move faster? So glycophorin. Okay. Does anybody disagree or agree? Well, everybody should raise your hands because those are two choices. Disagree. Everybody disagrees or agrees. Does anybody disagree? Okay. And why?
Because alkaline phosphatase is only bound to one side of the leaf.
So it's
only in one side rather than going through the entire.
So it's got two fatty acid tails. It's a standard phospholipid anchor. What can move faster through a viscous environment than a fatty acid? Nothing can move faster. So it's zipping around. It's like a little kid standing in the membrane waving a balloon, right? So the little kid can walk around really fast because just his feet are in the lipid bilayer. But if you're a transmembrane protein, most of you, the alpha helix is flow. You have to go through this viscous lipid bilayer. This alpha helix has to push through all those lipids. So consider the viscosity of the two environments. The protein is in the aqueous environment. There's nothing that's viscous about that. It's low viscosity. The protein is the little boy's balloon or kid's balloon, right? But the alpha helix is having to wade through muck. So the way this is going to look is this is going to be alkaline phosphatase, and green is, they're both going to go to 100%, but alkaline phosphatase is going to get there a lot faster. Now, what would happen if, let's say 20% of the glycophorin, remember it goes up and down, is bound to the cytoskeleton like it actually is in a red blood cell. It's actually tethered to spectrin. So we're going to say 20% is stuck to spectrin, the other 80% is moving around. How would that change the curve? So this is 100%. It's going to go, so remember, the 80% represents the amount that it rises, and the gap between 100% and where it stops, that's the part that's bound. Okay? So it's got to go up to the 80% mark, and 20% of it here is stuck to something and immobile. 80% of it's fluid. So that's how you read this graph. Okay, any questions? Okay, good. Now, let's go on. And we have other techniques. There's a whole large variety of techniques. Remember that FRAP is a population study. You're not looking at just one protein, so sometimes it's kind of cool to look at a single particle. Actually, the meeting I went to in December in San Francisco, it was a joint meeting about biophysical techniques and cell biology, and one of the coolest things was looking at individual RNAs, individual proteins, individual membrane proteins. So you can actually stick a little sphere onto an individual protein. And then you can actually track that with a laser, and you put that sphere on there because if you laser the protein, you're going to destroy it. And so you track that sphere and it's reflected light, and you can see where it's moving. Okay? And so you can tell by the different movement patterns what's going on in the membrane. So over here what you've got is, here's a completely random. It's just moving around. It doesn't stay in any particular place. If it's random, it's not tethered to anything. It's just free to move. And then you could test that by using FRAP and show that the whole population of this protein typically recovers to 100%. So that would corroborate that hypothesis. What if it starts here and it just goes like a beeline, it goes like that? What does that indicate to you? That's not random, is it? What could give it a hitch, a ride like that? What can make it move in a directed way? Microtubules? Okay, well, close. That's the highway. What's on the highway? Motor protein connected to the membrane protein. So you could just zip straight to a destination. So directed motion tends to be mediated by connection to a motor protein. And remember, the actin cytoskeleton is highly concentrated underneath the plasma membrane. It's called the cell cortex. And there's a reason it's concentrated there, because motor proteins are moving stuff on it. Okay. So directed motion, that indicates that it's probably a cytoskeletal mediated event. Okay. And then we have these complicated patterns where it kind of goes all over and sort of stays in an area, and we call those areas either domains or corrals. It's like a little corral. And those corrals are made by cytoskeletal proteins underneath the membrane that restrict. So if this is a transmembrane protein, it's going to interact with spectrum, and it'll stay there for a little while, and then it'll escape. Okay, so let's look at this picture. So that's what's happening here. So it starts out here. This is not random, is it? I mean, it's not going all over the place like this, and it's not staying in one area, so it's not immobile. What it does is it goes here, and it's encased in a little corral, and it bumps around, and it finally bursts through, because the halftime of these proteins interactions, they're fairly fluid. Okay, so then it goes into a new corral, bumps around, goes in here, bumps around, goes there, and so it's going into a different domain, and that's because in this kind of membrane, that's your corral. Okay, so what's happening is it's starting out here, and it stays in this corral, and then it manages to go through into this one. It bumps around for a minute, and it goes over here. So it's partial confinement is what it is. And the confinement is the cytoskeleton underneath the cell membrane. And it's supposed to be that way. Okay. And this is obviously a really complicated story. So, all right, so let's talk about types of confinement. One is that bacterial rhodopsin sort of aggregate. So if the proteins self-aggregate, that will make them so big and so heavy they won't move. So self-aggregation is a way of making membrane proteins immobile. Okay. And the reason you do that in the bacteria is you're basically making a photovoltaic cell that's receiving sunlight and converting it into a proton gradient. Okay. All right, so let's look at this one. So membrane protein can bind to proteins on the outside of the cell. So remember, proteins in the extracellular matrix actually help hold cells together into tissues or into epithelia. Like what's holding your gut lumen together is that it's attached to an underlying thing called the basal lamina. And these are extracellular matrix proteins like collagen that it's getting a hand grip on. So the transmembrane protein is reaching out and grabbing onto it. That's going to lower its mobility if it's bound to an extracellular matrix protein like collagen. A classic molecule that does that is called integrin. Okay? It's a transmembrane protein. It's really immobile because it's actually anchored to the cytoskeleton on one side of the membrane, and then on the extracellular side, it's grabbing on to a protein called fibronectin. So it's anchored on both sides because it is there to hold that cell where it's supposed to be. So you can have membrane proteins binding to extracellular or intracellular proteins, and then you can have this type of arrangement. This is a junction between two cells. And let's see, I don't know if I have a picture of an epithelia. No. Yeah, there we go. So that's a tight junction. And this is, we're going to talk a lot about the intestine because it's a really simple way to think about transport. But so there's the lumen up here. The nutrients are coming up here. This is the blood. You don't want everything in your gut lumen sneaking into your blood, right? Because some of it's nasty, all right? You just want the good stuff and the rest of it goes out, okay? And so so the way the intestine operates is I keep everything out unless I have a protein to bring it in. And so the reason it keeps everything out, I'm talking about water, generally even most iron, sometimes it'll let an occasional ion through there, but that's a tight junction. And that prevents stuff in the lumen from sneaking into your bloodstream accidentally. Okay, and so these two cells are basically holding hands. Go back to this. And so you have a transmembrane protein on cell A holding hands with a transmembrane protein on cell B. And it makes a zipper, and it's in 3 dimensions. It's a belt all the way around, kind of like one of those plastic things in a 6-pack of Coke, right? And little things sticking up where you open it, that's the short side so that's the head of the Coke can, and everything below here is in a separate compartment below, in your cooler, I guess. But what's sticking them together are purposeful interactions, cell-to-cell proteins touching each other. Okay. Questions about how things might aggregate. And clearly that's going to affect the FRAP measurements. It's going to affect single particle track. If you label a tight junction protein, what's its little thing going to look like? A little single particle tracking. It's like, duh. It's just going to stay there. And then what would its FRAP profile look like? Flat. Exactly. If you zapped it, it would just stay white. No recovery. Okay, good. So we can learn a lot by biophysical techniques. Okay, so that brings us into the real topic and this is where we're starting to get into function and medical applications, and so, because there's a lot of pharmaceuticals targeted towards transport proteins throughout the body, so it's important to understand how these things operate. And so we'll just briefly, actually, I think this would be a good point to take a break. And what I'm going to do, so Bailey's going to come up, and I need people to come up and remove your recorders. Yes.
Maybe it's easier if I walk around and just say the number of the group.
Oh, okay. That's fine. Then you can just leave those. Okay, let's do that. So Bailey will say the group number, and you come to her, and she'll hand your papers as a group. Okay. But you're free to talk and everything. At least one person has to pay attention to what you're doing. And if that person is not here, please do not take the paper and give it back. One question on the test was thrown out because there was no correct answer. And what happened was, and this is something you should understand about my test. When I do my key, what I do is I have the right answer somewhere. And then what I do is I pick a random number between 1 and 5 and assign it to every problem. So I randomized the placement of the correct answer from A through E. Right? So if you go like, guys, there's 3 in a row that were C. That can happen, right? Just random choice. So if you're detecting patterns in the way I'm putting things, and students do this, it's just psychology. You know, they go, oh, I can't put another C there. It happens, okay? So don't do that. I randomize it, but sometimes it gets me into trouble because the question where it was on, exchanging the estrogen and glucocorticoid, that question, it should have been B and D, but B and D is not on one of the answers. So what I did was I still gave you 21 questions. So in other words, each question was only worth, instead of 5 points, which would have been if I just threw out the answer, the problem, it's actually 4.7. So it's, you lose less points. And then I gave everybody that the credit for that one problem, since you had to waste your time reading it. So yeah, I mean, so you should have gotten 100 if you answered everything except that particular question. I think it's like question 14 on green form. So nobody lost points on that. In fact, everybody gained 4.7 points. Yeah, it's question 13. And then I think it's 4 on the blue form.
Is the extra 4 points reflected on Blackboard, or?
Yeah, no, I added it before I posted it. Yeah.
You're going to post like a key or something?
I am going to post a key now that you have it. And before you come talk to me about your test, really what you should do is look at that key and try to understand why you missed what you did. That'll give me a much better heads up on where the problem is. And in fact, you should always do this. The other thing, your test is really a valuable learning tool. It's not a game and then the season's over. What I'm trying to do with each of these quizzes is get you to the point where you're going to take the final exam by yourself, and you will have covered all that material several different times. So don't look at this as if you really screwed it up, right? There are ways to recover. In fact, that test can be dropped and replaced by your final exam. But your final exam is going to be an individual test. So it's going to, that's what we're preparing for. So look at that test as a way to get better each time, and not as I just failed. You know, if you look at it that way, just don't look at it. And the people that don't pick up their exams are classic examples of that. You can't get any better. You got to sit there and figure out what it is that I missed. What's my plan to prevent that? And then you got to carry it out. And you do this over and over and over. And you do it throughout the time, not just before the exam. You do it as you go along. That's how you get better. But the test is to improve your skills, not to give you a bad grade. Okay. Okay. So our goals in the transport area are these 4, and so we'll start with these, the top 2. We need to classify proteins into useful categories. You should be able to do that already, but we'll go quickly over it so you can remember what those categories are. And they may be slightly different than Dr. Dini's, I don't know. He usually asks me when he's developing his, so we're pretty consistent. And then we're going to illustrate transport mechanisms with real examples. So we're going to look at real poster children that actually do this, and many of them are targets of medicine or pharmaceuticals. Okay, so protein-free lipid bilayers are essentially impermeable to ions and to a lot of things. So the cell's idea is the lipids make everything impermeable, and then we put proteins in to bring the stuff that we want. It's kind of like the intestine. We put proteins in there that specifically transport the stuff we want. Everybody else stays out. So that's the idea. So there's 2 different main classes of membrane transport proteins, transporters and channels. But that's actually not where you start in dividing proteins and transport processes into categories. What you start with is the energy that they use. So is it passive or is it active? That's the two categories. Just like integral membrane peripheral proteins, we're going to use energy as our first split in the road. Okay. All right, so what things are passive and what things are actually transported? Well, you have to be really small, like a gas, and really nonpolar to diffuse through the membrane by simple diffusion. Don't say ever passive diffusion. That's like saying diffusion. All passive, everything passive is diffusion. So passive diffusion is redundant. So simple diffusion means it gets across with no help from a protein. And the only thing that can do that on a reasonable basis are these guys here. Okay? Now we move in, if you're really small, but you're a little bit polar, the membrane does not like you, and you have a very limited permeability, but there'll be some small amount that can diffuse across the membrane without the help of a protein. But you know what? You know, in your kidney and where these three compounds are actually transported, they use a protein. There's a water channel, there's urea channels, and there's a glycerol channel. They're all called aquaporins. So the kidney says that's not fast. That diffusion rate is too slow. So we're going to speed it up and use it actually as a channel. Okay. Now, if you're any bigger than this and you're polar, you don't go across. It's almost that's actually finite. That level of simple diffusion is finite, but it's tiny. It's kind of like the K-cat. It's really small. Okay. And by the way, most transport processes follow Michaelis-Menten kinetics, so you don't have to learn any kind of new kinetic program. Okay, so if you're going to get glucose and sucrose because they're large and polar, you need a transporter to do it, some sort of protein. Okay. And then finally, ions, even though they're really tiny, but they carry a full charge, they don't go across at all. So you need channels or transporters to get them across. You must have a protein. So that's the basic rule. All right. Now, I said that when you're splitting transport processes into categories, the first big two categories are based on energy. Is it diffusion or is it active? Is it passive or active? Okay. Now, so this thing, this is a sodium ion or it's a monovalent ion, and you need to look at the gradient to be able to tell whether it can diffuse across the membrane. Now, based on what I've just told you, this is not going to go across at all if there's no protein because it's charged, right? So there must be a protein pathway. So that's a given. It has to have a protein. But even if you put, let's say, an ion channel, like a sodium channel, and you open it, okay, which way would it move? Well, that's pretty easy to tell because, number one, there's no membrane potential. Okay? If you put an electrode into the earth on this side of the membrane, and that's usually the default, the outside of the cell is taken as ground, and it's connected to a wire that runs into the ground. Okay? And you put the other electrode inside of the cell, this is telling you that there'd be 0 millivolts difference between those two. There's no electrical potential. So that makes your job really easy as to which direction this is going to move. So if you open the ion channel, this is going to move into the cell because chemically it's higher on the outside than it is on the inside. We don't need to worry about the charge. It's going to move driven by the chemical potential. All right. But that's rare. What is the charge? What's the membrane potential on Joe Blow's cell? And I apologize to people named Joe. What is it? The outside is always 0. So it's always something on the inside with respect to the outside. Yeah, it's this. It's negative on the inside. And if you had to pick a number, minus 60 millivolts is how the displacement of charge is across that membrane. So now the sodiums are more concentrated. They're less concentrated. So the chemical potential is going to move it in. But there's an electrical potential. Now, is that going, so if it's more negative on the inside than the outside, will it attract that positive charge? Yeah, this is just really simple. You open the ion channel, and this is more negative, that's positive, so it's both. The electrical potential and the chemical potential are saying, come in. Okay? So those are two easy cases, and you don't need any math to do that. You just do it by inspection. What about this situation? It's more concentrated on the outside than the inside, but the inside of the cell is now more positive than the outside. You open the channel, which way is it going to move? Can you tell? Absolutely not. You have to have something called the Nernst equation to figure that out. And we'll get to that, how you use that. But there are some cases where the electrical potential is opposing the chemical potential, and then you need some help to convert one of those potentials into the other. And we'll do that. Okay? It's really straightforward. All right, so here's our sort of diagram, and you should do this as a concept map. Passive and active are the two categories. Under passive, you have three different things that are going to split off from that. No protein, simple diffusion. It's not passive diffusion, it's simple diffusion. If it's a protein, you've got two choices. It's either a channel or a transporter. Fundamentally, they operate very differently. Okay, and I'll show you why. If this is passive transport, this must be a uniport. It transports one type of solute. Now, I'm not talking about the stoichiometry. I'm talking about it transports one type of thing. Glucose, amino acids, something else. It's always transporting one solute, not two different solutes. Okay? So that's this side. Now, the other big branch is the transport from our concept map. So if it's active transport, it means you're having to add energy to the system to make it move against its electrochemical gradient. That is, it's facing an uphill gradient. That's what we usually call it. And it could be because of the electrical charge or the concentration, but it's going uphill, right? So you have two ways to deal with that. Number one is you can split ATP and couple the splitting of ATP to the movement of the solute and pumping. And guess what? We call those transporters pumps. So everything on this side, the active transport, is called a transporter. But there's different flavors. Okay? If it's a pump, we call that primary active. And that's because, let's go back, that's because the pump splits ATP itself. It's an enzyme. Okay? Now, so that's primary active. Okay? So if there's primary, there must be secondary, right? And secondary is where there's no ATP split by the transporter. Instead, you're coupling, that is, you're moving together two different solutes. One solute is going down its electrochemical gradient, and it's pumping out the other one. So one's going against its electrochemical gradient, and it's piggybacking. It's actually a slacker. It's a hitchhiker going off the energy of this one that's coming down its electrochemical gradient. If they go in opposite directions, so the characteristic is no ATP is split by the transporter, and it must be two or more solutes, two or more different solutes. Again, we're not talking about stoichiometry. We're not talking about two sodiums or two potassiums or two calciums. We're talking about a sodium goes in and a glucose comes out. All right. So if they go in opposite directions, you call them an antiport. If they're going in the same direction, you call them a symport. Right. Now, some biochemical texts consider things like the sodium pump, which is moving 3 sodiums in exchange for, 3 sodiums out in exchange for 3 potassiums coming in. They call that an antiport. I do not. It's in a completely different category. It's in the pump category. It's not in the coupled transport category. Okay. The only thing that can be an antiport or symport, they have to be secondary active transporters. Okay. What's the other port? The uniport, and that's back in the passive section. Okay. Channels are facilitated diffusion. Okay. Okay. So, yeah, that's what this shows. So, a uniport, that's a type of so-called facilitated diffusion. The word facilitated is to distinguish between the two types of passive transport mediated by a protein. Okay? You either have a channel, that's facilitated diffusion, or uniports, that's facilitated diffusion. Okay? So uniports are all passive. Symports and antiports are all secondary active. They involve two or more solutes moving in the same or different direction. Okay? So that's the rule. So now you have this entire chart you can lay out. Okay. All right, so I just bring this up again. Generally, the kinetics for all of the transport we're going to talk about, with the exception of ion channels, is nicely described by Michaelis-Menten kinetics. So they're very specific, they saturate, they have a Vmax, and they have a Km that is sort of inversely proportional to affinity. So you don't have to learn anything new, thank goodness. Okay. So let's go into specific categories and start talking about poster children. Okay. So we're going to talk about passive transport. We're going to talk about facilitated diffusion and uniports, not channels. We're going to talk about channels are fairly complicated, so we talk about them at the end of the transport section. Okay. So we have two different solutes, and they're not called substrates. They're called solutes in transport land. Okay. Substrates are for enzyme land. Okay, this is a different thing. All right, so the GLUT family stands for glucose transporter. That's what the GLUT stands for. And it was an early, it's one of the first membrane proteins discovered. The first one was isolated from red blood cells. They all have the same, they're all about 500 amino acids. They all have 12 membrane-spanning alpha helices. And the N-terminus is on the cytoplasmic side. So where's the C-terminus? So here's the rule. If it has an even number of alpha helices, the C-terminus is on the same side of the membrane as the N-terminus. That's a speed read for you. So if the N-terminus is on the inside and it's got 12, the C-terminus must also be cytoplasmic. And it's important to know which side they're on. Okay? If it's an odd number, the N-terminus and C-terminus are on different sides of the membrane. And you should draw a cartoon and convince yourself of that. Okay? But it's nice to have that inside of your head so you can quickly deal with that. Okay? So look, this is very specific. This is the Km. So when this number is small, it has high affinity. When that number is large, as you know, it's got a sloppy affinity. Okay? This thing loves glucose. The Km is 1.5 millimolar. But look what you're doing. If you take this is the chair configuration of glucose. If you take this hydroxyl and move it up here, it's now called mannose. Look what that does to the Km. The GLUT will not move it. It doesn't like it. So understand that the solute that you're measuring is going to change the Km of that transport process. If it's designed to move glucose, it's probably going to have a very low Km with the natural solute. And if you put an imposter in there, it's probably going to be poorer affinity and higher Km. So that's a good rule. Okay. Now, there are actually 12 different, I think maybe 12, there may be 14 now, different GLUT molecules. And we're only going to focus on these 5. Because they illustrate. And we're going to use every one of them to do something useful. Okay, so this was the first one identified, so they called it GLUT1. It was identified in red blood cells. Most of your cells have GLUT1, with a few exceptions. So it's the Joe Blow, whatever, surrogate. But anyway, GLUT1. Now look, Km, this is measured by this weird stuff. Is this glucose? No. It's modified so that it cannot be metabolized. And that's to help the researcher not lose some of the glucose due to metabolism. So if you're measuring glucose coming into a red blood cell, and the glucose comes in, and that's what you're measuring, and some of it is converted to carbon dioxide through metabolism, that radioisotope is going to leave. It's going to be blown off. You don't want that to happen, so you use this sort of weird non-metabolizable analog as a proxy for glucose. But look what it does to the Km. Remember, the Km for GLUT1 for the native glucose is 1.5. If you use a weird stand-in, it's still recognized as glucose, but look, It's gone up to 7, so it's sloppier. But it's, as long as we use the same solute for all of these things, we get a pretty good estimate of the changes in Km. So these are all isoforms of the same 12, 12 membrane spanning alpha helices, but they do different things, and so they have slightly different sequences. Okay, GLUT2 is expressed in the intestinal cells that absorb nutrients, facing the blood side. Look at that. It's got the worst of the affinities of all of these, 13. So it's got a sloppy affinity for glucose. GLUT3, that's in your brain. Okay? The brain is the prima donna. It has the lowest Km, the highest affinity. It takes its glucose off the top, because if it doesn't get glucose, you fall over. Right? So that's why it wants extremely high access to all the glucose. GLUT4, this is the one that's regulated by insulin. The reason your blood glucose drops in response to insulin is because GLUT4 is moved to the plasma membrane. It's trafficked to the plasma membrane and inserted there. And its Km is sort of intermediate, it's 5. GLUT5 is the last one we'll talk about. It's located in the enterocyte on the luminal side, facing the gut lumen. And look, what does this tell you? It's got an infinite Km. It's actually a fructose transporter. So when it does not bind at all to glucose. So one of the GLUTs is actually a fructose transporter. Okay? And that's what happens if it has a really ridiculous Km, then it probably is, that solute is not a transporter for that particular protein. Okay? Now, can we make sense out of this? Yeah, let's do this. All right. So the question is, why is this affinity so sloppy and this one so high? It's the order in which your body gets glucose. Where do you get glucose? Not through your skin, right? You eat it. It goes into your intestine. So the highest concentrations of glucose that you will ever see are inside the gut lumen. And so why make a GLUT transporter that has a high affinity when you don't need it? So that's sloppy for a reason. That's the average concentration of glucose that this transporter receives. And that's generally how they evolve. They represent the time average concentration that transporter encounters in its position in the cell. That's usually what the Km means. Okay? So where does glucose go next after it leaves your gut? It goes into the blood, right? Let's go up to the blood. So look, 13, now we're going down to 7. The affinity is getting higher. So your red blood cells, and by the way, most other cells, are going to suck that glucose away from the intestine. And so as the affinity increases, you're increasingly taking glucose and using it by pumping it, or not pumping it, but bringing it into cells. Where does glucose go after it gets into the blood? Well, your body goes, it reads your blood glucose and it releases insulin, and it goes to 2 places: skeletal muscle and adipose tissue, unfortunately for some of us. And skeletal muscle is actually the major consumer of blood glucose after a meal. And so look at the affinity. You go from gut to blood, down even further to skeletal muscle. So your skeletal muscle is going to suck in the glucose and store it as glycogen to reuse when you're not eating. Okay, so this makes physiological sense. And then finally, your brain gets its cut off the top. So as soon as it gets into the blood, who's going to suck it up? Your brain, because it will not function at all if it doesn't have glucose. It can, but it's rare. But so it's really sensitive to low glucose, and so it has the highest ability to suck glucose out of the blood. Okay, so this makes sense. Any questions about that? Okay. Okay, so so we talked about the nature of the solute. We talked about the type of protein that does this. Now we're going to look at the mechanism. This is called the alternating conformation model. This is a uniport. So what happens is it oscillates between 2 states that's driven by the solute binding. Okay? So the solute, it can face the outside, and this is actually called the T1 conformation, transporter 1, facing the outside of the cell. The solute binds. That causes the transporter to refold. It assumes the T2 conformation. It faces the cytoplasm. The release of the glucose causes the protein to refold again back to the original conformation, the unfolded carrier. This is a little bit more detailed, okay, and that you can go through. So T1 facing the outside, glucose binds. The binding of glucose causes it to undergo a conformational change. This is the alternating conformation, okay? It's driven by solute binding. So when it faces the inside, the cytoplasm, it's in the T2 configuration. It loses the glucose. The loss of glucose causes it to refold from the T2 back to the T1. This last refolding step of the unloaded carrier is the rate limiting step. It's the slowest because there's no solute to really kick it between the two states. Okay. So that's the mechanism. Okay. Any questions about how that works? Okay. So there's nothing real tricky here. Okay. So we're illustrating transport mechanisms with real examples. So we've done the GLUT family, and now we can move on to active transport. We'll come back to channels because, again, as I mentioned, that's a little complicated, and so we'll deal with it a little bit later. So now we're going to go to active, and the first question you have to ask, are we going to start with primary or secondary? And we're going to start with primary. That means exclusively we're talking about pumps. Okay. And so that means they must have an enzymatic activity and a transport activity because they have to be able to split ATP. That's the hallmark of a pump. Okay. Again, we're lucky they conform to Michaelis-Menten kinetics. Now, which is faster, a pump or a uniport? We can actually, this is a nice point in which to write this down. Okay. So the rule is the pumps, because they have to split ATP to do their job and they're pushing something uphill, they are slow. So it's pumps, this, and it's anywhere from 1 to maybe 1,000 ions per second. Slow, very slow. Transporters, like the GLUTs, are faster. But again, remember, it's only driven by the concentration gradient or electrochemical gradient. So they're either about 100 to maybe at most 10,000 molecules per second. Okay, so they're faster, but not really fast. Ion channels are the fastest. When they open, things fly through there. The rate is 10 to the 7th to 10 to the 8th ions per second. So pumps are slowest, transporters are next, and then ion channels are the fastest. Okay. And that has to do with the mechanism by which they transport stuff. Okay. So there's 3 classes of ATP-driven pumps, and we won't get through all of them, but let's do a couple of them. Okay. Everybody got that? Okay. The best one, best understood one, is the calcium pump, and this particular pump lives in 2 places. And again, for all of these transporters, know the location. It's like real estate. You got to know where the location is that it operates in order to understand the function. So it operates in 2 places. It's on the plasma membrane, where it takes calcium from the cytoplasm and pumps it outside the cell. The direction of active transport is very important. Okay? Next is the ER, the smooth endoplasmic reticulum. It takes calcium out of the cytoplasm. See that you notice that's always the same. It's always reaching for the cytoplasm and taking it into the exoplasmic compartment. So it takes calcium out of the cytoplasm and loads it into the lumen of the ER, which is the exoplasmic compartment. The reason it's doing that is high calcium in the cytoplasm is only there for a small period of time as a signal. If that calcium signal stays up too long, the cell kills itself. High calcium means cell death. Okay? Yes, ma'am. Which one?
I said it's only in the smooth one.
No, it's actually also, it's the same, pretty much same protein. It's in the plasma membrane. Okay. When it's in the smooth plasmic reticulum, we call it SERCA, smooth endoplasmic reticulum calcium transporter, or calcium pump. On the cell surface, it's usually called the calcium ATPase. But they're essentially the same protein. Okay. Okay, so here's how it works. And again, there's two conformations, and the enumeration is exactly the same. When it's facing, this is the cytosol, okay, and then we're going to pump the calcium into the ER lumen, which is below the luminal, the ER luminal cell membrane. Okay, so it's facing the inside of the cell in the E1 conformation. It can either be loaded or not loaded to ATP, but this thing is not going to split ATP until what happens? The solute has to bind into this binding pocket. Two of them. The stoichiometry here is important. Again, this is not a uniport, this is a pump. So 2 calcium ions load into this binding pocket. That is the signal for the ATPase to split ATP. And when it splits ATP, it releases the ADP into the cytoplasm, but it holds on to the phosphate because it actually phosphorylates aspartic acid residue. That's kind of weird. Most phosphorylation events in the cell are added to what amino acids? Tyrosine, serine, threonine. Aspartate is very special. It's used in this pump cycle. Okay, so you phosphorylate that aspartic acid. That induces a large rotation of this little guy called the activator domain. In some textbooks, it's called the actuator, which is actually a better mechanical engineering term. It causes this thing to spin by 90 degrees, and that is what flips this from the E1 conformation to the E2 conformation. So now the binding site for the calcium actually collapses and ejects the calcium into the lumen of the ER. Both calcium ions dissociate. The leaving of the calcium, these are 4 positive charges. If you lose that many positive charges, you're going to actually strongly affect the conformation. And what it does is it causes that phosphate to be dephosphorylated. You split that covalent bond so that aspartate loses the phosphate group, and it goes back into the cytoplasm, and it converts this from the E2 back to the E1. You now have an open binding pocket, and you're ready for the next set. So it's going E1, E2, E1, E2. Now remember, if you take this pump and you put it in a vesicle, in the Golgi, because it has to go all the way through those membrane organelles to get to the plasma membrane, always remember the ATP must be on the cytoplasmic domain. So it's going to, if this is the calcium ATPase, that's the cytoplasm, and this is the outside of the cell. It's always moving calcium from the cytoplasmic domain to the exoplasmic, and you won't get confused. Okay, so for example, if this, and I'm running out of transparency tape roll here. So if this is a cell, and I said, okay, here's a vesicle, and then there's a SERCA here. Okay, which way is it going to transport? Well, the ATP has to be in the cytoplasm, so it's going to take ATP and split it, ADP, okay. And then the calcium is going to be pumped out of the cytoplasm into the exoplasmic compartment, which is the lumen of that vesicle. And this is going to fuse with the plasma membrane, and that's how you deliver the pump to the plasma membrane, is exocytosis of this vesicle. And so again, ATP will be split like this, and calcium will be taken and ejected outside the cell. So you can operate this on the plasma membrane, in vesicles, in the Golgi, in the ER, all the way through the cell. But just keep the orientation straight. And looking at where the ATP binding domain is, that's going to help you get it right. Any questions about how this works? Okay, good. Now, let's do So let's do another one. And we're going to use the same kind of idea. And I like to use this diagram because it's so bad that it teaches you what the actual structure of this protein looks like. This is the sodium pump, okay? And what's wrong with it? Okay, number one, this is an alpha subunit, not an A subunit. So they're Greek letters, and these are labeled with A and B because the artist didn't know what he was doing. And so each one of these subunits is actually capable of transporting sodium across the membrane, just like that calcium thing was. All of these, the calcium ATPase has about 10 membrane-spanning alpha helices. This has multiple membrane-spanning alpha helices. You don't need to memorize how many there are, but there's like 6 to 10. Okay, that has 6 to 10. This has 6 to 10. Okay. And each one of them, as I said, is individually capable of moving 3. So it doesn't take both of these together to move 3. Each of the subunits can move 3. Okay, 3 sodiums outside. So this is the inside of the cell, and so this is where the ATP is going to bind. So this must be the cytoplasm, right? All right. This beta subunit is, and again, it's beta. This is a single pass membrane protein. So why is that wrong? Well, they drew it wrong. Okay, so it actually spans the membrane once. It's there for targeting this to the correct position, which in all cells is the plasma membrane. You don't put the sodium pump 2 different places. It's always on the plasma membrane. Okay, so this is a bit more complicated because it's going to actually take 3 sodiums and eject them, and then it's going to take 2 potassiums and bring them in. Okay? But we're going to do the same stuff. We're going to phosphorylate our cells on aspartate and do this same kind of switch around. Okay, so we start up here at the top, and okay, that's probably all right. The initial state, E1, means the ATP binding site and the sodium binding sites are facing the cytoplasm. Okay, so the first thing that happens is usually ATP is loosely bound to the beta subunit, or I'm sorry, the alpha subunit, and we're not going to say any more about the beta subunit. Okay. So what happens to get it the ATP to fire is 3 sodiums bind to the E1 conformation. That causes that ATPase to split the ATP, and again, it releases ADP and hangs on to the phosphate. That's critical. It changes from the E1 to the E2, and in the E2 conformation, the sodium binding site is facing the outside, and so it releases the sodium, and what happens is it actually picks up 2 potassium. So if you eject the sodiums, it actually changes its conformation, and now it has a high affinity binding site for potassium. The potassium loads on, and that is the cue for the protein to refold. It refolds by stimulating the dephosphorylation of the pump. So the loss of that highly negatively charged phosphate causes the E2 conformation to refold back to the E1. So you're going from E1 to E2, back to E1. Okay? So you lose the phosphate, the thing refolds, the potassium binding sites now face the cytoplasm and they dissociate, and the binding site for sodium is now reconfigured, and you're ready for another round. Okay? Okay, one other thing is in many cases, we'll use pharmacological tools to probe the presence of these things. And the thing that's going to bind to this and block it is called wabane. And wabane actually binds near the potassium binding site and blocks this thing. Okay, let's stop there and